My name is Nicola Franco, and I'm a research engineer at the Fraunhofer Institute for Cognitive Systems. It's a pleasure to present our work at the International Symposium on Software Engineering for Adaptive and Self-Managing Systems. Here is the title of our short paper, Towards a Self-Adaptive Architecture for Federated Learning of Industrial Automation System, together with my colleague, me, Marc, and Gereon. So here the agenda. First, an introduction to the federated learning approach, the problem formulation, our approach, the map-K loop, preliminary results, and future direction. So, we start, what is federated learning? We consider distributed system composed on several devices, which are connected to a centralized cloud server, where each device has a local dataset composed by measurements and labels. At the first step, each device receives a model from the global server and then update the model according to an optimization technique with its local datasets, like the stochastic gradient descent method. And then in the third step, each device sends back the model to the central server for the federated aggregation, and then loops back again several times according to the accuracy that I need for the training procedure. Okay, so in this case, we formulate the problem in the industrial domain and looks like as follows. So we have a loss function defined as a fi for each factory, when we want to minimize the sum of all of them with respect to the model. If we consider that each factory is a bunch of smart industrial devices, then the problem looks like as follows. So we want to minimize the loss function, in this case the LJK, so between device J and subset K. So we split the datasets of the smart factory into a number of subsets equal to the number of devices that we can see in the next slide. So we have all the devices on the left hand side and the dataset on the right hand side. The assumption here is to have a shared knowledge. In this case, the knowledge is the datasets of the factory. And each device of that factory can access all the datasets and compute a loss function in each part of these datasets, split into a number of subsets. And the problem looks like as follows. So we have a sum, as before, in this case, between all the edges. So all the edges that go from the devices to the subsets. And this sum is made from a loss function times a decision variable that takes value only 0 and 1. And this P is a vector of all the decision variables, which are constrained according to two constraints. The first one means that each device has to be assigned to at least one subset, and the second constraint means that each subset has to be assigned to at least one device. Okay, so in this case, the framework for federated learning in the industrial domain looks like as follows. So we start from the federated aggregation. We solve the previous problem through the centralized optimization. Then we train the model according to the solution of the centralized optimization. Then we can do a local iteration or move to a global aggregation, so in the cloud server level. And let's have a look at the decentralized optimization, how we solve the previous problem. We can rewrite the previous problem in terms of linear programming by just using this vector notation where the L means all the loss functions. It's a vector of all the previously computed loss function for all the devices in all the subsets times the vector of all the decision variables. And the matrix A takes into account all the constraints, and the B is a vector of ones. We exploit the distributed simplex algorithm, and so just to give you a rough introduction, this matrix Hj is composed by the loss function of the device J and the constraints of the device J. And this Bj is a base and comes from the big M method. So we use the M in order that is the highest value in the processor times a vector of ones. And this is the identity matrix. So these B and J are updated accordingly to a lexicographical order, and the base is shared between the devices. After this procedure, then I have my solution, so where I should train the model. So these matrices are taken into account on the centralized optimization function that is explained inside the paper. And alpha gives you the solution of where I have to train the model in the next iteration. Let's look at the map K loop in order to better understand the concept behind. So we have several devices, one factory, and the datasets share the dataset of the factory share between all the devices, where each device has a neural network model. So we start from the monitoring phase, so it means that each device computes the loss function in all the subsets, and the mean between all the subsets, all the loss function computed in the subsets for the device J. We analyzing by taking the minimum of the loss, so it means that it's the best model that has the minimum loss function and the minimum loss. And we can choose between a global aggregation step or a decentralized optimization. So we split again the dataset into the number of devices, and then we run again one decentralized optimization, and we update the model according to an optimization technique. In our case, the stochastic gradient descent method. Okay, so preliminary results. We have compared our model with a benchmark, the federated averaging between different factories and different devices. So in this case, we have 3 to 5 factories and 10 to 15 devices. This has been implemented in MATLAB. We can see in the graph that the federated averaging is faster, and we are considering that the federated averaging is taken into account in all the devices and all the factories without using any decentralized optimization technique, as in our case. And we can see in our model that it jumps from from local iteration to a global aggregation and reach a higher accuracy due to the assumption that we have a shared knowledge on the devices, on the factory. So the future direction are test our model on different datasets and models, try with identical and independent distributed datasets, non-identical and independent distributed datasets, implement adversarial nodes that try to mislead training, and take into account asynchronous aggregation, so sending the model to the central server at different times, and possible communication errors. And I finished. Thanks for watching.